All right, so today we are going to begin our analysis of the frequency response of transistor amplifier circuits. And before we get into this, I want to cover Miller's theorem. I think that's all we're going to talk about today is Miller's theorem. It's a couple of sections into the chapter in the textbook, but I feel that it merits its own little section because of how important it is and how much we are going to use it. It seems like you guys should really understand what the hell is going on. Otherwise, you're going to be just crazy lost. So with that in mind, let's talk about Miller's theorem and apply it to a couple of quote unquote difficult transistor circuits. All right. So Miller's theorem says that if I have a floating impedance, so let's say that I have some node in a circuit with a voltage V1 I have some impedance Z like so, and I have another node in my circuit with a voltage V2, and both of my voltages are measured with respect to ground. I need to put one constraint on my voltage V2. And that constraint is that the voltage at node 2 is a scaled version of the voltage at node 1, okay? So if we know some fixed relationship between the voltage at node 1 and the voltage at node 2, we can apply this guy, all right? So we can observe that there is some current I flowing through our impedance from node 1 to node 2. Miller's theorem says that I can replace this floating impedance with two impedances. I can effectively split it up into two pieces. And that transformation looks like this. So I still have my voltage here, V1. Now I'm going to have some impedance Z1, which I will define what it's going to be momentarily. We'll talk our way through it. I'm going to have another impedance here, Z2. And I still have my relationship V2 is equal to K times V1 here, but now I have a current of I1 flowing, and now here I have a current of I2 flowing. So to recap, Miller's theorem says that we can replace a floating impedance Z with two impedances, one placed between node 1 and ground, and the other placed between node 2 and ground. My impedance Z1 must have a value of Z, my floating impedance, divided by 1 minus K, and my impedance Z2 must have an impedance of Z divided by 1 minus 1 over K. So let's talk briefly about why this works, because we are going to exploit the bejesus out of it over the next several weeks, okay? So for our original circuit, The only way that node 1 can tell that there is an impedance connected to it is by the amount of current that's being drawn away from node 1, right? If that were impedance were not there, meaning there were an open circuit, there'd be no current there. The magnitude of that impedance determines how much current I flows from node 1 to node 2. So if we want to break this guy into an equivalent circuit, we need to do something to force the same amount of current to be leaving node 1 while maintaining that exact same voltage so that node 1 experiences no difference, right? So that gives us the constraint that our current I1 has to be V1 divided by Z1, that's just good old Ohm's law, must be identical to our current I, which is given by V1 minus KV1 divided by Z. And I'm just going to group like terms here real quick. I have V1 times 1 minus K divided by Z. Okay. So again, I'm just saying that my new current I1 in my right-hand circuit has to be identical to my current I in my left-hand circuit, and I've drawn a mathematical relationship. Well, if we look at this guy right here, and this guy right here, our left-hand relationship, we have a voltage V1 divided by some impedance Z1, and our right-hand relationship, we have a voltage V1 divided by some other impedance. We can set those two impedances equal to each other, and that is where we get the relationship that Z1 is simply equal to Z divided by 1 minus K. Easy enough, right? We're going to use the same constraint, meaning that that current I2 in our right-hand circuit has to be the exact same thing as our current I in our left-hand circuit as well, in order for these guys to be electrically equivalent. So that gives us I2 is equal to negative V2 over Z2, which is in turn negative K V1 over Z2, has to be equal to I, which we know to be V1 times 1 minus K over Z. And so this tells us that Z2 is negative K Z divided by 1 minus K. And if we divide the numerator and denominator by K, this gives us Z over 1 minus 1 over K. I see an incredulous look here. So let's go back. Skipped a little bit of algebra, but let's go back one. All right. So if I divide both things by K, I have numerator and denominator by K. I obviously have negative Z in the numerator, and then 1 over K minus 1. I multiply that negative 1 through, giving me Z over 1 minus 1 over K. That's what happens if I don't skip the math. All right, so we have a means by which to split up any impedance. Yes, ma'am?
So when you say floating impedance, it means it's not ground?
Yeah, so it's between two nodes, and neither of those nodes is ground. Absolutely. So let's put this into practice, and I think you'll get a better feel for what I mean by a floating impedance. All right. Her. So let's say that I have a simple common emitter amplifier. Here's some resistance RC. Here's transistor Q1. Here is my output node, the out. Here's some resistance RB. Here's where I'm applying my input. And I'm going to put in a resistor here, RF, that is between what we'll call node X and my output node. This resistor RF, or this feedback resistor, which is tying the input of the BJT to effectively the output of the BJT, would be considered a floating impedance, having a value of RF. Now, if we tried to analyze this guy using the circuit analysis techniques that we've learned prior to learning about Miller's theorem, this becomes a massive headache because we have this coupling thing that's tying our input to our output, and it makes it extremely hard for us to develop relationships that separate our input and output, right? So for a problem like this back in 335, what we did was something of the form of, we said that our voltage gain was V out divided by Vx multiplied by Vx divided by Vn, right? If there were no feedback resistor there. And that was an easy enough way to figure out what was going on. But we have this feedback loop that is preventing us from doing something as simple as this. This is where Miller's theorem comes in, okay? So we are going to make an assumption here. Let's see. The first assumption that we are going to make, if my pen thing will write, is that VA is equal to infinity, so that we can ignore the early effect, although in this particular problem, it's not going to be that much of a pain in the butt if we had included it. And our second assumption is that we're going to say that our feedback resistor is large enough that V out over Vx is approximately equal to negative GMRC. So we're saying our feedback resistor is large enough that we could kind of sort of consider it like an open circuit. It's still going to have some effect, and that's what we're going to figure out what's going on. But we need to have some V out over Vx relationship here because we're using a resistor. How we're going to be applying this in our frequency analysis is typically over capacitors, where we're going to be able to use our simple DC voltage gain relationships to not have to constantly have some other crutch helping us with the math here. But I'm just trying to illustrate something that's going on. So our goal is to find AV, the relationship between V out and Vn, okay? So I can use Miller's theorem and split this resistor RF up into two resistances, right? So let me show you exactly what I am talking about here. So if I drew, without accidentally moving to the wrong page here, here's my input voltage. Here's my resistor RB. This is node X. R pi. Here's V pi. Here's my ground. Here's GM V pi. Here is resistor RC. And out here, I'll put V out. Now, as it's drawn right now, our resistor RF is between our base node, which is at X, and our collector node, which is at our output, meaning that we have some resistance here, RF. And it should be fairly obvious just looking at this thing. We can see right now that finding a relationship for our output voltage is going to be made much more difficult by the presence of this feedback resistor, right? If we apply Miller's theorem, we get to delete this resistor RF and instead place a resistor between node X and ground. I'm going to call this guy RFA, and between the output terminal and ground, and I'm going to call this guy RFB, and I have to save and restart. This is going to make this circuit much, much easier to analyze, right? So for example, what could we find to be our output voltage now effectively just by inspection? So negative GM V pi RC in parallel with RFB, right? All of this current is going to flow down, then flow back up through these two resistors here because of Kirchhoff's current law. These guys are just simply in parallel. So Ohm's law tells us that we have negative GM times V pi because the positive polarity terminal is on top and the current's flowing into the negative polarity terminal. So that's easy enough. How do we find V pi in terms of Vn? Voltage division, right? So V pi is the voltage drop over RFA in parallel with R pi, right? Because RFA and R pi are in parallel. They're both placed between node X and ground. So that is going to give us Vn multiplied by RFA in parallel with R pi, divided this by RB plus RFA in parallel with R pi. And we can now substitute this equation into our first equation and determine our voltage gain. AV is V out divided by Vn is going to be negative GM RFA in parallel with R pi multiplied by RC in parallel with RFB divided by RB plus RF A. Sorry, I couldn't read my writing. Divided by R pi. Let me erase this, or excuse me, in parallel with R pi. And boom, we have analyzed a circuit that in two steps that would have been extraordinarily difficult to do otherwise. Nathan, what's up?
When calculating RFA, are we gonna have to do some weird things? I'm still trying to like understand the current one.
Okay, so RFA, exactly right. Yeah.
I don't know how we tell.
Yeah, so RFA is our original RF divided by 1 minus our voltage gain, effectively. That's that K factor that's relating V1 to V2, where in this case, V1 is the voltage at node X with respect to ground, and V2 is the output voltage with respect to ground. So we'd have minus negative GMRC, looks like 1 plus GMRC. For RFB, we're going to have RF divided by 1 minus 1 over negative GMRC. So if I multiply through by goodness gracious, what is going on here? If I multiply through by GMRC, I'm going to get GMRC RF over 1 plus GM RC. And I would just substitute that in directly into my previous equation, and I'm done. Did that answer your question at all, or did I? That's the gain. That's relating the output at node, or relating voltage X to voltage V out.
Okay.
Because I was literally told. Yeah. So Vx is node 1, V out is node 2. So K is the gain that tells you how Vx is either amplified or attenuated to form V out. Right.
Would it be advantageous to, once you have your initial value of AV, to use iteration to try and get more accurate by getting a more accurate value of RFA, RFB, not using the assumption negative GMRC or V out over VX?
I do think that it would be advantageous and more accurate. So the issue here, I'm doing this with resistors because I'm not quite ready to dive into doing things with the capacitors and all that kind of stuff. With the capacitors though, so I guess what I'm trying to avoid is something that you guys kind of observed when you did your first design project for this class, okay? So let me pull up LT Spice real quick. We're gonna take a brief aside today and intro what I'm gonna talk about on Monday. Here's LT Spice. File, open, design problem 1. All right, so this is, can everybody on Zoom see this? Doesn't tell me I'm not screen sharing, so I would guess so.
Yes.
Okay, cool. So this was design problem 1 with the correct resistor values and all that jazz, or somewhere close to this, which you guys should have all arrived at. If I run this simulation, and I figure out where I put my keyboard and potentially my mouse. And I plot my voltage gain here. Right, so this is a plot of the voltage gain. Let me change this signal to be not green, so it's maybe a little bit easier to see. Let's see, tools. Okay. All right, maybe this is a little bit easier to see in here. The bright green to me seems hard to see from this close, so I imagine it's a pain in the ass for you guys. That's a little. This was a common emitter amplifier, right? we designed it to have a specific voltage gain of approximately 7 decibels. But we only see that the voltage gain is around 7 decibels when our frequency is larger than somewhere around 1 megahertz, right? So all of the small signal analysis that we've done to this point is technically only valid in what we're going to call the mid band, okay? Below the mid band, we are going to see that the capacitive effects of our bypass and coupling capacitors and stuff like that dominate, which is why we have this weird frequency response over here on the left-hand side. And on the right-hand side, after our mid-band, which isn't going to show up on this because it's using an ideal MOSFET, but you guys observed in your electric files and all that kind of stuff with the parasitic resistances, this guy fell off rapidly beyond a certain frequency as well. So we only have a mid-band where the voltage gain is exactly what we calculated it and how we've been calculating and all that stuff is applicable. Then we have a low frequency band where our coupling capacitors and all that kind of stuff dominate what's going on. And then we have a high frequency band where the internal capacitances of our transistors start dominating everything. So when we are dealing with the circuits in both the low frequency band and the high frequency band, it's perfectly reasonable for us to use our DC approximation for our transfer function between those two node points here. We're skirting around that because we're dealing with resistor only circuits right now. But once we get into the circuits where we're including all the capacitors and all that kind of stuff, those DC gain relationships that we developed are exactly the relationship between node X and the output node. So we don't have to rederive all that crap again. So today is more of an exercise. So you're 100% correct. You could iterate on it now that we know what the gain is and try to better estimate what our Miller resistances RFA and RFB will be. But when we get into the nitty gritty of actually analyzing the frequency response of transistor circuits, that's pointless because that feedback resistor doesn't exist. So did that illuminate things? Okay. All right. So let's circle back around. So that example was fairly easy. Let's look at one that's a little bit harder. That was a, let's see, common emitter amplifier. Let's switch modes to MOSFET and look at a common drain, so a source follower. So we're going to take our output at our source. This is transistor M1, where we're going to assume our channel length modulation coefficient is 0. Our feedback this time is going to be between our base and our source. So let's call this guy RF. Our input is applied over here. Here we have RS. Let's call this guy node X. And we are making the assumption here that RF is large enough such that our relationship V out over Vx is approximately that of a source follower. So that would be RL over RL plus 1 over GM. All right, so I'm not going to draw this guy with the feedback resistor in as it's drawn. I'm just going to move straight to the Miller approximation, which is going to look something like this. So we have our input voltage. Here's RS. Here is node X. So between X and ground, I'm going to place a resistance RFA. Node X is also the gate voltage for my transistor. So here I'm going to have VGS. This is my source. Here I have GM VGS. My drain is tied directly to VDD, so that's going to look like a small signal ground. Now, yes. Beats the hell out of me. Let's change it to RG. I think I had RS as a source resistance, but I can definitely see why that would be confusing. So let's move it to RG. That's a good call. Measuring my output here. And then between my source and ground, I'm going to have my load resistance. I'll put that over here on the right-hand side, RL. And I'm also going to have my other Miller resistance. So I'll call this guy RFB. So let's start with a simple question. Did I split my feedback resistor up correctly? Do I have one resistance between node X and ground and the other resistance between node out and ground? Yeah, okay, so that's done correctly, all right. It should be fairly straightforward to see what our output voltage is going to be on this guy again. So somebody tell me what that is. GM VGS times RFB in parallel with RL. And so now we struggle potentially with how to figure out what the input stage does to quantify that. Okay. Anybody have any thoughts? So the current flowing through RFA.
We didn't know that. We don't know the current going through RF, so we don't know the current going.
Yeah, that's fair. Yeah. Any other thoughts? We're trying to get the voltage gain, so we need to know an input-output relationship. Right now, we have things in terms of VGS. I like where your head's at. Let me say that. So what is VGS by definition in this circuit? Vx minus Vout, okay? So GM Vx minus Vout times RFB in parallel with RL. And I'm going to move a factor of negative Vout GM RFB in parallel with RL over to the other side, which is going to give me Vout times 1 plus GM RFB in parallel with RL is equal to GM times Vx times RF2, just give me B in parallel with RL. That's what I get when I mix my subscripts up. Now, do we have enough information to figure out the relationship between Vx with respect to ground and Vn with respect to ground? Absolutely. It's the voltage division you suggested we do a minute ago. So this is going to look like GM RFB in parallel with RL multiplied by Vn times RF1 over RG plus RF1. And so our voltage gain V out over Vn is going to be, yes. Thank you. That's the only place I screwed that up, right? Yeah, okay. So I'm going to have this as GM RFA divided by RFA plus RG multiplied by RFB in parallel with RL, all over 1 plus GM RFB parallel with RL, where RF1 is simply RF divided by 1 minus RL over RL plus 1 over GM, and RF2 is RF over 1 minus the reciprocal of that guy. So that's going to be RL plus 1 over GM divided by RL, which is going to turn out to be GM times RL times RF. Yeah, no. Sorry. A and B. There we go. I apologize. All right, so that one was a little bit more difficult, but not wildly so. Let's crank things up a notch one last time. And this will be the last thing that we're going to talk about today. All right. So we have done a common emitter because it was a BJT. And we did a source follower, an emitter follower would have been effectively the same thing. Now let's do a common base where we're no longer going to neglect our early effect. Transistor Q1. Now our early effect resistance, R out, is going to be our feedback resistor. If you recall, this is something the textbook said was too hard to deal with, which is why for all the common base amplifiers, you never see anything in the textbook with regards to what happens when the early effect is included. We are going to make the assumption that V out over Vx is approximately GM times RC. So we're saying that our early effect resistance is very large in essence. And our goal is to, again, determine the new approximation for the input-output relationship with the early effect included. Yeah. Yeah, why can't we? Yeah, so this is what's going to allow us to simplify some circuits. And this one's probably going to make it the most obvious is what we're going to do with capacitors and all that kind of jazz. But anyway, all right, so I'm going to draw this guy with the Miller resistance is already in place, so my base terminal is grounded. So here is resistor R pi. Here is voltage V pi. Here I have GM V pi. This is my emitter base. So over here is my collector. My collector sees that resistance RC between the collector and ground. I'm also going to see a resistance R0B between the collector and ground. And here is my output. At my emitter, I have that resistance RB. Here's where I apply my input signal. And then I also have a Miller resistance of R01. So this guy is fairly complicated. There are two ways that we can approach it. The first of which is finding the voltage gain directly. The second is finding the short circuit transconductance and the output resistance, and then effectively multiplying those two because we know that that's going to be the voltage gain. So which of those two methods do you guys want to do? They're both roughly equally annoying. Pardon? All right, short circuit transconductance, more straightforward. All right, so we will go that route. Absolutely.
So how do you always done like A on the left circuit and on the side, but I'm doing time. How do you know?
So I've been putting, I mean, I have been putting A on the input side and B on the output side every time, because I know the relationship. I know that B is the voltage at B is a scaled version of the voltage at A because it's an amplifier. So I'm saying that my output is a scaled version of my input, which is why I'm always putting B on the output side and A on the input side. Does that make sense? Yeah. All right.
So going on to that line RB for the large, like through
I have no idea. All right, so let's give it a letter that doesn't suck. Let's give it how would RE suit you? Okay. Yeah, I don't know why. Oh my God. All right, okay. Are we good now? Okay, thank you both for nitpicking. I'm sure I deserve it. So, all right, so if we were to determine our short circuit transconductance, let's see. I would be grounding, let me put this right here, right? I would be grounding my output terminal and then measuring the current that's flowing in. So I'm going to draw a simplified version of just that network, recognizing that if I ground my output node, R0B is ground on both sides, RC is ground on both sides, so those guys go away and I don't have to think about them anymore. So let me just write here, GM. All right. So I have my base is grounded. Here is resistor R pi. Here is voltage V pi. Here is resistor RE, which I'm going to have to carry through. Here is resistance R0A. Here is GMV pi. and this guy is grounded, right? And I'm trying to find I out. Well, it seems pretty darn obvious that I out is just GM times V pi, right? And then that current is going to split up and flow through my resistor network, right? So I can say, hold on, let me, all right. I'm going to redraw this guy one more time real quick to make something else super duper obvious. Here is V in. Forgot to draw resistor RE. So here is this node. Here is R naught A. Here is R pi. And my negative polarity voltage is here. So here is V pi. And then my current is flowing from ground so this is going to be GM V pi, and this guy right here is still just I out, right? This is going to help me calculate, in my opinion, V pi pretty dang easy. Okay, so recognizing that I out is just GM V pi, we can figure out what V pi is just using good old voltage division right here. Because I have R naught A in parallel with R pi in parallel with, what's this guy going to look like? 1 over GM, right? Because the current flowing into the, sorry, those both look like negative. The current flowing into the positive polarity terminal is GM V pi. The voltage drop over it is V pi, so it looks like 1 over GM. So that is going to be negative GM Vn R naught A in parallel with R pi in parallel with 1 over GM divided by RB plus R naught A in parallel with R pi in parallel with 1 over GM, giving us a short circuit transconductance of negative GM R naught A in parallel with R pi in parallel with 1 over GM. And then we have RB plus R naught A in parallel with R pi in parallel with 1 over GM. So we have half the work done. Because, sorry, stop scrolling. So the question that was asked is, why do I make this negative? Because voltage division tells me that if I have the positive polarity of this guy on bottom, I would expect to get positive polarity on top, negative polarity on bottom when I do voltage division. But I'm looking for negative polarity on top, positive polarity on bottom, which is where that negative sign comes from. Does that make sense? All right. Okay. Output resistance. So let's look back up here real quick at our original circuit. When I am measuring the output resistance, what do I do to this guy? Ground V in, look in through that terminal. So I'm going to wind up applying a test source to this guy right here. When V in is grounded, I should easily be able to see that R naught A, RE, and R pi are all directly in parallel, right? Okay. So that leads me to the following simple circuit. Here I have R pi in parallel with RB in parallel with R naught A. This is V pi. Here's GM V pi. Here's RC. Here's R naught B. Here's my output node, so I'm going to apply some voltage, Vx. Measure the current, Ix. All right. So should be fairly straightforward. Ix is going to be Vx divided by RC in parallel with R naught B. So I'm just taking care of the amount that branches off and flows through these two guys in one fell swoop, plus GM V pi. Just good old Kirchhoff's current law. GM V pi, or actually, excuse me, V pi is my current Ix minus Vx divided by RC in parallel with R naught B. So I'm saying how much has branched off and flowing through that node multiplied by R pi in parallel with RB in parallel with R naught A. So that's just an Ohm's law representation of that voltage drop. So the voltage drop across those three resistances in parallel is those three resistances in parallel multiplied by the total current flowing through that branch, which is just Ix minus how much split off. That back in, what I am left with is Ix is equal to Vx over R naught B in parallel with RC plus GM times Ix minus Vx over RC in parallel with R naught B. Everything multiplied by R pi in parallel with RB in parallel with R naught A. Moving my Ix terms to the other side. This gives me Ix times 1 minus GM R pi in parallel with RB in parallel with R naught A. Draw, there we go. Is equal to, so I'm going to have Vx over RC in parallel with R naught B minus GM Vx multiplied by that parallel combination. Effectively what I'm getting at is I have a common denominator of RC in parallel with R naught B here that I'm going to be working with. So I will have Vx one minus GM R pi in parallel with RB in parallel with R naught A. All of this over RC in parallel with R naught B. R out is equal to Vx over Ix. So somebody tell me what that's going to be. Sorry, what was that? So it's not gonna be 1 over, right? So divide both sides by Ix, I have Vx over Ix here. If I divide both sides by this guy, it's like multiplying by the reciprocal. So I'm gonna have RC in parallel with R naught B on top, and then the same thing. So RC in parallel with R naught B, which gives us an overall voltage gain AV of V out over V in is the same as negative capital GM times R out. So capital GM had a negative sign, so we ditch the negative sign, and we have GM R naught A in parallel. Let's see. Parallel with RB in parallel with R pi divided by RB plus R naught A in parallel with RB in parallel with R pi. This whole thing multiplied by RC in parallel with R naught B. And then because we know that, where was it, way up here? Our K in this case is GM times positive GM times RC. R naught A is going to be R naught over 1 minus GM RC, and R naught B is going to be R naught over 1 minus 1 over GM RC, multiplying through by GM RC on the numerator and the denominator gives me GM R naught RC all over GM RC. Yes, sir.
So when you use the voltage gain expression in the capital
Yes, yes. Okay, I'm sorry. Yeah, that was me not looking up enough. Yeah, so everywhere I have RB, thank you, Brian. Everywhere I have RB right here should be 1 over GM. Thank you. One over GM, 1 over GM. There we go. Thank you for catching that. The minus sign for here.
So, at the bottom, when you did the gain, pulled it out. Or was it already made? AV was before negative GM and then.
So yeah, so AV is equal to negative capital GM, and capital GM is a negative quantity because we saw that there was a negative sign out front. So those two negatives cancel each other. That's all that was. All right, so you guys feel comfortable-ish with applying Miller's theorem, splitting up feedback loops and all that kind of good stuff. All right, so on Monday, we're going to get into our frequency analysis. We're probably going to do some low frequency analysis and then get into the high frequency models of our transistors, which is where we're going to see lots of weird capacitors between terminals, which is why we need to use Miller's theorem to make these things remotely manageable. So, all right, you guys have a good weekend and all that jazz, and I'll see you on Monday for oh so much math.